Hello, in this video we explain the logistic regression algorithm for classification and its implementation in Python. So for the logistic regression, it's a model to estimate the probability for the event, or we say this is a positive event which we focus on. For example, we are interested in the patient has specific kind of symptom, disease, so the probability of this is the positive event. And first we have to understand what is odds. So if we have a p for probability for this positive event, and 1 minus p is the probability of negative event. So for example, p is the probability have cancer, and 1 minus p is not cancer. So the division of these two, called odds, is the ratio between positive events probability and the negative event probability. And the logit, we often hear what is the logit. Logit is the logarithm of the odds, or say log odds. So logit p equals the log of odds. And logit p also equals the net input. So what is net input? If we want to model the probability, so we have to take into account the sample data. So there are features of the observations for each person. For example, their weight, their age, their other characteristic information. So this is the feature x1 to xm, and this is the weight parameter and plus the BS. So weight parameters are what we will train in the model to estimate, right? And the product of feature and the weights and plus BS called net input. So this net input equals logit. So logit of p equals net input. So net input is a linear function usually. The sigma of w, weights and feature and plus b. So it's quite clear. Odds is the ratio between two probabilities, and the log odds is the logit. Logit also equals the net input. So next, but we know the logit, but this is this is a quite simple form because logit equals net input. But we are more interested in the probability of the positive event, right? So we take inverse of the logit function and we'll get the probability. So this sigma z called activation function, it is also equals the positive events probability. So this value is between 0 and 1. It is the division between 1 and 1 plus e minus z. So here e is the scalar and 2.718, right? Is scalar, and minus z. So z is the net input. So z is this part, say net input. So in other words, for one person, we have information of this person's say net input, and put this net input in this form, we'll get the positive event for this person, right? For this observation. So for each observation, different net input will get different probability of the positive event. And this form is the logit form. This is the Sigmoid logistic sigmoid function. Usually call this sigmoid function. So the logistic regressions procedure for update the weights can be shown in this figure. We get net input for one observation, then sigma together net input. Then using sigmoid function, get the probability for the positive event for this observation. then compare with the observed value y equals 1 or 0. 1 represents the positive, 0 represents not positive. So compare this, we can get the error. And from this error, we will get the likelihood function, and also the loss function will be trained, updated with respect to this weight value. So after training finished, we get the final weights and BS. Then we'll take a threshold function to get the predicted 0 or 1. So from this line, this vertical line, this part is the training part. So next we will talk about the likelihood function. So every machine learning training will use optimization technique. So they are loss function. And in logistic regression, also the loss function is connected with the likelihood function. So likelihood function actually is the negative of the loss function, because likelihood function is the product of all the conditional probability. So what is the conditional probability? Conditional probability is from given information, feature, and what we will estimate the parameter, then we'll get this observed y value. So if we make this term the product for all the samples as big as possible, this is what we want to see. This means the model is performs better, right? So what we want to see is we have a model, we know the feature, and we estimate the parameter. Then from this information, the positive events will be closely as possible to this observed probability. So the product of all these observations, because we assume that all the samples are independent, so we can project all these together, get a likelihood function. So it has the form activation function, sigmoid probability of positive, then yi in the power, then times 1 minus for the negative, 1 minus I in power. Together product, this is projection symbol, this is likelihood function. But if we use this likelihood function for type of loss function, just use a negative symbol, then it's quite difficult to do optimization, because this scary project, right? So one manner is to take logarithm for this function. So the logarithm of this likelihood function called the log likelihood function. And actually it transforms the projector to the summation. So from 1 to n, each sample we have these two terms summation together. So for the learning rule is we will initialize the weights and the BS with 0 or small random number. Then for each training, here will be all the training samples in each epoch. We will compute the value of the sigmoid activation function A, then update the weights. So what this means? This is for one sample. For one sample, will have some effect for the weight. And this is for these samples feature for these weights. So there are 3 weights, for example, there are 3 features, right? So J from 1 to 3. So for each weight will has 1 feature. Then times the observed positive value, observed class label 0 or 1, then minus the probability for the positive event. So this is A. A is actually is the sigmoid function's result. This one, this is A. This is A equals sigma Z. So we calculate each observation's probability for the positive event, then for this corresponding opposite of the value y, there is the error. Then times feature, then times learning rate. At that very small number, can update weight. So actually, this is only for one observation, but actually we use all the observations in one epoch, so update weight one time in each epoch. Similarly for the BS term. So this is the learning rule. So after the predetermined epoch finished, then we get the final values for the weights and the BS. So next, we will show how to implement such an algorithm for logistic regression in Python. And if you are interested, you can get the files, Python files from this link. So we go to Python load. From this file, we load all the required packages or modules. Successful. Can just skip this part. And we use iris data set. We can load iris. This procedure have been shown many times in the previous videos. So we just do it quickly. So create the features and the labels. Then we take train test spirit for 30% of the samples as testing sample and testing set and 70% for the training. And we use stratify equals y. Then we can show the print the correct for the original data label 3 classes, each with 50. Then in the training 35, and test set 15. Perfect. Then we normalize or use standard scalar function for the training and testing set. So they have same scale now. We just skip the perception because we have shown this algorithm in a previous video. We will come back later for this plot decision region. This function will be used for many videos, but we will come back it later. So here we use Sigmoid. So first define a Sigmoid function equals 1 divided by 1 plus sigma minus c. Then next we just show how it is going for the sigma function of values between minus 7 to the positive 7. We show this result. It is S-shaped. So when C will be very large, so the sigmoid function's result will be close to 1. This is the probability from 0 to 1. Then we define the loss 1. Here we show 2 demo loss function. See here because here we want to show loss function for the actual value is 1 or actual value is 0. Then for the different value, different net input, how it is going with the probability and with the loss function. It's not so direct with our algorithm later, but here you can see if, for example, this is the positive. So actually, this is positive 1. The label is 1. The label is 1. If the net input is very large, then the loss will be 0. Because the net input is very large, which means the probability for the positive event will be very large. And very large for the model's probability, and actually the label is 1, so the loss is 0, right? Is correct. And if here this side, if the say value is very small, net input very small. Net very small means we get a very small positive event probability from the model, from the sigmoid function. But actually the label is 1. So, which means the error loss will be very large from this blue line. And on the contrary, this red line for real observed label is 0. 0, if label is 0, but we have very big net input here, so which means we get very big positive event probability from the model, but actually the label is 0. So which means error or the loss is very large, right? So this figure just shows for this mechanism. So next we will create a class for the logistic regression gradient descent. So here parameter eta is a learning rate, very small number, then iteration, and the random state used for the random number generation. And attributes weight, BS, losses. So weight is when the array, how many features, there were how many weights. And the BS is one number scalar, and the losses with underscore is a list for each epoch's loss. Then for the initial function inside this class, we'll set learning rate, iteration, and the random state. Then the fit function is for the training. So here the input is feature X, the array shape is how many samples, observations for the row, and how many features for the column. So actually here we use 2 features because it's easier to show in the plot decision function. So this is the training data, and Y for labels is when the array with the how many numbers for the sample. Then we set random number state, then create normalized initial value for the weights using this random number generation, and with the shape as training data's second axis, which means the column number. And BS is a float number 0. Then create an empty list for losses for each epoch. Then for loop for each epoch, we will first get net input from X. Net input is a function. Net input function here we can see net input is the product between feature and weight. So here is the matrix multiplication, then plus a BS. Then output is actually here is sigmoid activation of net input. So here also a function called activation. So activation is a sigmoid activation function. 1 divided by 1 plus exponential of, here we use a clip because we do not want to get very small, very large numbers. So we just cut these two to the limit on both ends. So we get the activation, then the error is Y. This is label minus probability. So if we look at here, Y minus probability for the activation. This is the result of sigmoid, right? So this is for, and of course here is the y is not one observation, it's for all the observations. So minus all the output from all the sample, right? And then update the weight. Update, this is delta. So this is the update part equals eta times x is the feature transpose, then multiplied with this error, then divided by shape, divided by how many sample size. And BS is similar, but here no x, just eta times error. Then the loss is loss function. We have to show here 1 minus y dot output minus 1 minus y dot log output, then divided by shape. Then we append this loss in this epoch loss in this list. So this is the training function and the net input activation function, and another is the predictor function. Predictor function is the activation for the net input. Then if this probability larger than 0, we will set the label 1. Otherwise, it will be labeled 0. So here is the model output probability for positive events. They're quite understandable. So because we will use this predictor function in the plot decision function we'll show later. So we just run to create this class. Create it. Then we set X string, Y string for a subset. Because logistic regression only for the 2 classes, and the Elis data set has 3 classes. So we use the first two classes for the training. Then we can create an instance of this logistic regression class. Successful. Then we can use this class's fit function. Successful. Then we will use plot decision regions. Then we go back. So plot decision region function, it is actually doing 2 things. So we first define different markers, different colors, and we did a map for the color. Then first we plot the decision surface. So what is decision surface? Decision surface is a map. But we will show from the module, if we assume there are millions of points on this map. This map is 2-dimensional, right? It's a rectangular map. And we will show the result of the predicted label from this module, from what we have trained the module. Then for this millions points input, what is the predicted label for the y? Then for the logistic regression, here will be 0 or 1, right? So we will show different colors for different label from the module prediction. And a second job in this function is to show the actual points from our sample. Also show different shape, different colors for the 2 label classes. So we will see if the observed value stay on the same region from the module's decision region. This is the idea of this function. So we just run this successful, then come back to logistic. So we could show plot the decision regime of the train subset, then classify this logistic regression we have shown. So this is the decision regime from this map with the red area, blue area, and these points as observed points for the two classes. So it says the module, this is the module part, can predict the real points 100% correct. So in this video, we have just showed the very basics of the logistic regression algorithm. And if you are interested, you can take a look at detail for this code and come back to our video later. Thanks for watching.